Chapter 12, this is about liquids, solids, and intermolecular forces. Gases are not here because we had a whole chapter about gases before. And this is a quote from Roald Hoffmann. It's a wild dance floor there at the molecular level. So here we're going to look at what does water look like in zero gravity?
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung out cloth? So, and I had to use equipment that was here on board the space station. We might have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's compacted. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck and you pull out your washcloth, this is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Merit and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water's all over my hands. In fact, it rings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is, the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jell-O on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
Now, I'm guessing that's not what you expected the water to do. Because what happens when we wring out of water a wet washcloth here on Earth? The water falls to the ground, right? And it leaves the washcloth. So he's doing this on the space station, no gravity. So there's nothing to pull the water down. And so the water has intermolecular forces that hold the molecules to each other. And so they don't want to let go of each other. And so it's going to move along his hands, but it's not going to let go and fall. So intermolecular forces are the attractive forces that are found between all molecules and atoms. Intermolecular means between the molecules. This is different than the bonds within a molecule. That would be an intraforce, intramolecular force. These are significant only at short distances, If it were not for intermolecular forces, there would be no liquids or solids. Everything would be a gas. And of course, then the universe would be a very, very different place. These intermolecular forces are essential for physiological processes. They're very, very important in how your DNA replicates and how your body uses enzymes and proteins. So the state of a sample is going to depend on the relative strength of the intermolecular forces compared to the thermal energy. So thermal energy causes molecules, atoms to vibrate and wiggle, to be like antsy little children, and they're just getting more and more antsy. And that's going to pull the atoms and molecules apart, whereas the intermolecular forces are trying to hold them together. And so whether it's a liquid or a solid depends on the relative strength of those opposing forces.